Hi guys, this is the EdExcel AS Level Further Maths Paper 2, taking a look at the Further Mechanics 1 section, and this is from the sample papers. Question 1. A small ball of mass 0.1 kilograms is dropped from a point which is 2.4 meters above a horizontal floor. The ball falls freely under gravity, strikes the floor and bounces to a height of 0.6 meters above the floor. The ball is modelled as a particle, and for part A, we have to show that the coefficient of restitution between the ball and the floor is 0.5. So, for part A, we have to first of all consider what would happen as the box is falling. So, as the box falls, of course we would have to use v squared equals u squared plus 2as. It's one of the Suva equations which you can find in the formula book. The speed as it hits the ground, we have v squared equals u squared, 0 squared, because it starts from rest, plus 2a, so we have 2g times by s, which is 2.4. So we have v squared, which is equal to 4.8g, and therefore v is equal to 4.8g square rooted. Okay, and now we can find out the speed once the box bounces back up. Okay, so let's just write that down. So after the first impact with the plane, the box rebounds back up. So the final speed obviously will be 0. And again, using v squared equals u squared plus 2as, we have 0 squared equals u squared minus 2g times by s, which is 0.6, and that's as the box bounces back up. And if we rearrange for u squared is equal to 1.2g square rooted, and therefore u is equal to u squared is equal to 1.2g, and therefore u is equal to 1.2g square rooted. And now for this question we would have to use Newton's law of restitution. Let's just write down the definition of that. So just as a reminder of what Newton's law of restitution is, that's E, and that's defined as the speed of separation over the speed of approach. And we've got the speed of approach, that's the square root of 4.8g, and we've got the speed of separation, that's 1.2g square rooted. And if we substitute these in, we have 1.2g square rooted divided by 4.8g square rooted. And if you work this out, you'd find we get 1/2. And that's exactly what we wanted to show. And now for part B, we are required to find the height reached by the ball above the floor after it bounces on the floor for the second time. Now, once it goes back up, it essentially goes back down, and it it bounces back down, and we have to find that height. So we already know that E is a half, and again we would have to use this. And if we call this time the speed of separation being v dash, and that's once it hits the ground and bounces back up, because remember it goes back down. It starts off this, so then it starts off at this, so it's approaching the floor again with this speed, and we have to find the speed when it bounces back up. So this time the speed of approach would be this thing over here. So now we have the speed of approach. The speed of approach, that's 1.2 g square rooted. So we have then 0.5 equals v dash. That's the new speed of separation which we are required to find, and then of course we'd be using this formula here, and then obviously we divide this by 1.2 g square rooted. Okay, and if we rearrange for v dash, you'd find v dash to equal 0.5 times by the square root of 1.2 g. And now if we use v squared equals u squared plus 2as, obviously when it goes back up we have that speed of 0 squared, and this is equal to this, essentially this initial speed. So we have 0.5 times by the square root of 1.2 g squared, and then because obviously we're taking downwards as positive for gravity, we have minus 2gh. We're finding h as well. So we have 0 squared equals 0.25 times by 1.2g minus 2gh. The g's can cancel, hopefully you can see that, and therefore if we rearrange for h is equal to 0.15 meters. Hopefully that's straightforward. And now for part C, we have to consider our answer to part B to describe the subsequent motion of the ball. Okay, so we've got this reason over here. So if you consider the ratios of the heights, initially we were told we have 2.4, then it goes to 0.6, and then it goes to 0.5. And what you'd find, considering the ratios of the bounces, we'd find we get a quarter. So that tells us that the ball continues to bounce with the height of each bounce being a quarter of the previous one. Question 2. A small stone of mass 0.5 kilograms is thrown vertically upwards from a point A with an initial speed of 25 meters per second. The stone first comes in to instantaneous rest at the point B, which is 20 meters vertically above the point A. As the stone moves, it is subject to air resistance. The stone is modelled as a particle. We have to find the energy loss due to air resistance by the stone as it moves from A to B. Well, the energy lost, that will equal the loss in the kinetic energy minus the gain in the potential energy. Let's just write that down. The energy lost is equal to the kinetic energy lost minus the potential energy gained. Now, kinetic energy, that's 1/2 mu squared. Potential energy, that's mgh. And subtracting these and substituting in the values, we have 1/2 times by 0.5 times by 25 squared minus 0.5 g times by 20. And if we work this entire thing out, we end up with 58.25, which if we want to write that to 3 significant figures, we have 58.3 joules. Now, for part B, the air resistance is modelled as a constant force of magnitude R newtons. We have to find the value of R for part B. For part B, we would have to use the work energy principle. Okay, and the work energy principle tells us that the change in energy, so the change in energy is equal to the work done on the particle. Okay, so we have the work done on the particle. So the change in energy, we've just found that to be 58.25 joules, and the work done on the particle, well, work done, that's defined as basically the force times by the distance. So we have 20, that's the distance, times by R, that's the resistance. And if we work out R, you'd find R to equal 2.9125 or 2.91 to 3 significant figures. And now for part C, we have to state how the model for air resistance could be refined to make it more realistic. So we can make the resistance variable. In other words, we can depend on the speed. Okay, make the resistance depend on the speed. Question number 3. We have a jogger who has a mass of 60 kilograms and he runs along a straight horizontal road at a constant speed of 4 meters per second. The total resistance to the motion of the jogger is modelled as a constant force of magnitude 30 newtons. For part A, we have to find the rate at which the jogger is working. Well, for part A, you'd notice if there's a constant force of magnitude 30 newtons and there's no other forces acting, the total force here in this situation is 30 newtons. And essentially, our driving force, you'd find that to be 30 newtons. There's no other forces and we have no acceleration as well. Okay, let's just write that down. We have no acceleration. And so therefore, to work out the power is equal to the driving force multiplied by the velocity. We've got this driving force 30, and we multiply this by the constant speed 4 meters per second. It turns out we get 120 watts. And now for part B. The jogger now comes to a hill which is inclined to the horizontal at an angle alpha, where sine of alpha is equal to 1/15. Because of the hill, the jogger reduces her speed to 3 meters per second and maintains this constant speed as she runs up the hill. The total resistance to the motion of the jogger from non-gravitational forces continues to be modelled as a constant force of magnitude 30 newtons. We have to find the rate at which she has to work in order to run up the hill at 3 meters per second. Let's draw this situation up. So we begin by drawing our hill. We were told that it's inclined at an angle of alpha, and if we quickly draw on the actual jogger like so, we've got, if I draw on the forces in a different colour, we've got this forward driving force Ft, we've got this resistance force 30 newtons. Of course, we've still got this reaction force. We'll call this reaction force FD. So we'll call this reaction force R. And then we've got the force of the weight as well, acting from the center. We have 60G here. And if we resolve parallel to the plane, what you'd find then is if we resolve parallel to the plane, you'd find FD is equal to 30 plus 60 G sine alpha. Now we were told G is equal to 10, so we have 30 plus 60 times by 10 times by sine alpha, which is 1 over 15. You'd find FD to equal 70 newtons. And we also know that the speed this time is 3 meters per second, and therefore, using this formula, the power is equal to FD times by V. So we have 70 times by 3, which is 210 watts. Question 4. A particle P of mass 3m is moving in a straight line on a smooth horizontal table. A particle Q of mass m is moving in the opposite direction to P along the same straight line. The particles collide directly. Immediately before the collision, the speed of P is u and the speed of Q is 2u. The velocities of P and Q immediately after the collision, measured in the direction of motion of P before the collision, are v and w respectively. The coefficient of restitution between P and Q is E. We have to find an expression for v in terms of u and E. So, for this question, I've drawn out the situation. We've got P and Q. Before, we have speeds of u and 2u in this direction, and that's before the collision. And after the collision, we have v and w, and notice the direction of the arrows. Now, we begin with this question by considering the conservation of momentum. Let's just write that down. Using conservation of momentum, considering what happens before, we have m times by 3m times by u, then minus, because we're going in the opposite direction here, m multiplied by 2u, and after the collision we have 3m times by v. So we have 3m times by v plus m times by w. And let's just clarify here. We have the situation before. Here we have the situation after. And you may remember Newton's law of restitution. That's defined as follows. For Newton's law of restitution, we have E equals the speed of separation over the speed of approach. Okay. Okay, so from this we can form an equation in terms of W, V, U for E. So we have E equals the speed of separation. If we consider the speed of separation, we have W minus V. Okay, and then the speed at which they're approaching at, we have U plus 2U. They're approaching each other. So we have 2U plus U. Okay, and essentially what we want to do over here, if we go back to the question, we want to find an expression for V in terms of U and E, and we've got an equation here in terms of M, U, V and W, and here we've got an equation in terms of W, V and U. Well, happily over here we can simplify all this to give us U equals 3V plus W, so the M's cancel, and then we can simplify the left hand side to give U. And if we look at this equation, hopefully you could recognize if we eliminate W from both equations, we'd then end up with an expression for V in terms of U and E. So if we call this equation 1 and this equation 2, our first step we want to eliminate W from both equations. Okay, so if we consider equation 1 and rearrange for W, you can see that W is equal to U minus 3V. And if we consider equation 2, we can rearrange. If we multiply both sides by 3U and then add the V to both sides, you'd find W to equal 3EU plus V. Okay, so we have 3EU plus V. We'll call this equation 3. We'll call this equation 4. And if we set equation 3 equal to equation 4, that will eliminate W. So we will set equation 3 equal to equation 4. And in doing so, you'd find we have U minus 3V equals 3EU plus V, and therefore we can rearrange this equation. First of all, taking all the V's on one side, we have 4V equals U minus 3EU, and of course if we factorize out a U, we have U lots of 1 minus 3E equals 4V, and dividing through by 4, you'd therefore find V is equal to U over 4 lots of 1 minus 3E. We'll call this equation 5. Okay, so now for part B of the question. Given that the direction of motion of P is changed by the collision, we have to find the possible values of E. Well, if P changes direction, then we can say from here that V will be negative. Okay? And if V is negative, remember we already know what V is. If V is negative, we set this to be less than 0. So we have U over 4 lots of 1 minus 3E is less than 0. And What we have to do in this part of the question is find a possible range of values for e. Well, if we solve for e over here, so let's just ignore the u over 4 bit, you'd find e to be greater than 1/3. And we already know that e must be less than or equal to 1. And therefore, in terms of our range of values for e, we have 1/3, which is less than e, which is less than or equal to 1. Now for part C, we have to show that w is equal to u over 4 lots of 1 plus 9e. Well, if we sub equation 5 into equation 3, we can find out what w is. So if we substitute 5 into 3, we have w equals u minus 3 times by u over 4 lots of 1 minus 3e. And if we factorize out a u over 4, we have u over 4 lots of 4 minus 3 lots of 1 minus 3e. So we have u over 4 lots of 4 minus 3 plus 9e. Of course, in conclusion, w is equal to u over 4 lots of 1 plus 9e. Okay? Now for part D, well, we'll call this equation 6 for now. For part E, following the collision with P, the particle Q then collides with and rebounds from a fixed vertical wall which is perpendicular to the direction of motion of Q. The coefficient of restitution between Q and the wall is F. Given that E is equal to 5 over 9 and that P and Q collide again in the subsequent motion, we have to find the range of possible values of F. Okay, so for this part of the question, let's redraw this situation. Okay, so I've just redrawn the situation, and if we quickly draw ourselves some sort of a wall like so. So what we have over here is a wall, and essentially once Q hits this wall, it rebounds back. So if it rebounds back, let's just draw on that rebound. It rebounds over here, and we'll call this speed at which it rebounds x. Okay, so this is the rebound. Okay, and having said that, we can first of all use the fact that E is equal to 5 over 9 to find out what the values of V and W are. Okay, so using the fact that E is equal to 5 over 9, so E equals 5 over 9, if we substitute this into our equation 5, so using 5, let's just underline this actually. Using 5, we have V equals u over 4 lots of 1 minus 3 times by 5 over 9. And if we simplify all this, you'd find we get minus u over 6. And if we use equation 6, you'd find w to equal u over 4 lots of 1 plus 9 times by 5 over 9 So we have 3u over 2. Okay, so we know that the coefficient of restitution between the Q and the wall is F. So what we have over here then is F equals the speed of rebound over the speed of approach. Okay. So we have the speed of rebound x, the speed of approach, that's, if you look over here, that's w. So hopefully that makes sense. So Q approaches the wall with speed w, it rebounds at speed x. And remember, we want to find a range of values for f. Well, first of all, if we actually determine what x is, we can see here x is equal to fw, and we know what w is already. W, we found that to be 3u over 2. So we have f times by 3u over 2. So we have x, which is equal to 3fu over 2. Okay, and we were also told that P and Q collide again in the subsequent motion. So having said that, if P and Q collide again, then we can say from here that x is greater than minus v. And that's because if we take left to be positive this time, obviously w is pointing towards the right, we see that x is greater than this speed over here. So we already know what v is. We found v to be minus u over 6. So we have x, which is 3fu over 2. This is greater than minus v, so we have minus u over 6. Okay, and in other words, you can see that 3fu over 2 is greater than u over 6, from which we can see f is greater than 1 over 9. And we also know that f is less than or equal to 1, and therefore the range of values of f, we have 1 over 9, which is less than f, which is less than or equal to 1. And that concludes the end of the paper.